I'm going to present local editing of cross-surface mappings with iterative least squares conformal maps. This work was conducted in collaboration between ETS, Concordia University, and Autodesk. Many methods yield cross-parameterization that are often globally good but can be locally wrong, for example, as we see here in the head region. We propose an approach to edit a surface mapping by locally adjusting them. In this case, we greatly improve the mapping in the head region. Computing a surface mapping between two surfaces is a fundamental problem in digital geometric processing. A wide range of methods have been developed to find surface mappings, but no single method results in a perfect mapping in every case. Quite often, the mapping results may be good overall, but some specific, sometimes subtle semantic features such as articulation and facial features may remain misaligned. Our approach complements these methods by editing the mapping where the user wants it. While a lot of research has been done on creating correspondences between 3D objects, comparatively fewer methods have been proposed on mapping editing. Panizzo and his colleagues proposed the weighted averages on surfaces framework. They use weighted averages with landmarks in order to define mappings, and then the user can improve the mapping by adjusting the landmarks. Although weighted averages generates good mapping results, its improved mapping application cannot use a mapping as input. Wester and his colleagues proposed an iterative filtering scheme based on the use of geodesic Gaussian kernels. An important restriction of their method is that it requires both surfaces to be discretized with the same vertex densities. Ezus and Benchen presented a method for the deep layering and denoising of functional maps. They smooth a reconstructed map by mapping the eigenfunctions of the Laplacian of the target surface in the span of source eigenfunctions. Their technique can be incorporated into existing functional mapping methods, but selecting the right number of eigenfunctions to perform the denoising is difficult. Compared with a ground truth mapping, increasing the number of eigenfunctions decreases the error until a minimum is reached, but adding more eigenfunctions beyond this point increases the error. While this can be observed on the ground truth mapping, there are no methods to achieve the minimum error for an arbitrary mapping. This is an overview of the most relevant methods. Please see the paper for a more exhaustive list of related work. Mappings computed by state-of-the-art methods are often globally good, but locally wrong in few areas which remain misaligned. Our approach is general and not limited to a specific initial mapping method. Since most state-of-the-art methods improve the mapping globally, this makes it hard for the user to fine-tune the mapping without risking modifying areas that shouldn't be affected. We propose a surface mapping editing approach providing local and precise control over the map adjustment. Here is the overview of our approach. Our approach is made of 4 phases. The input data to phase 1 are mesh A and mesh B, as well as mapping between the 2 meshes. In phase 1, we inspect the initial surface mapping between meshes A and B. The texture coordinate transfer is wrong because of the incorrect mapping in the ear region for this example. In mismatching regions, we select landmarks at locations that should correspond. Phase 2 provides segmentation for the local adjustment of the surface mapping. The segmentation phase has 3 steps. Step 1 grows an initial patch in 3D and 2D. Our main goal is to extract a single connected component. The initial patch allows for the planar parameterization. We grow an initial patch that interconnects all of the landmarks and has disk with hole topology. We flatten the patch in 2D during the planar parameterization step, where we have more tools available to control the size and shape of the patch. In step 2, we extract the polygons within or intersecting the convex hull of the landmarks. The convex hull step results in patches exempt of large concavities in their boundaries. We collect the polygons within or intersecting the convex hull made from the landmarks. Here's another example. The first step creates a patch with an artificial internal boundary which has a hole with polygons from the full mesh missing. In the second step, this boundary is filled by adding the missing polygons from the whole mesh. Step 3 ensures that we have enough polygons around the landmarks for the deformation step. We grow the compact patch from the previous step based on geodesic distance to allow enough room between the boundary and the landmarks. Phase 3 is about deformation. We edit the mapping by deforming parts of the meshes with respect to each other. We overlap mesh B on top of mesh A, and then we minimize a deformation energy to line up the landmarks to improve the mapping. We line up the landmarks by applying an energy minimization composed of 3 terms. The first term corresponds to positional user constraint for aligning the landmarks. The second term pulls the vertices of the boundary to the position where they correspond given the mapping. The third term is a distortion preventing regularization. An ideal deformation energy must meet 2 criteria: preserving the shape and maintaining the injectivity of the mapping so no flip triangles happen. For the deformation term, we experimented with state-of-the-art deformation methods such as LIM, SLIM, and KP Newton, but they were not satisfactory, so we developed a new deformation approach. ILSCM is a new deformation method where we iteratively optimize to decrease the LSCM energy. This iterative method uses the cotangent weight of the previous iteration for the deformation of the current iteration. Our new deformation approach also prevents flips from occurring. When lambda is small, the map will be injective, but the constraints are generally not satisfied. Conversely, when lambda is large, the user constraints are satisfied, but flips may be introduced. The idea is to adaptively adjust lambda to guarantee that we have no flips. In our experiments, we start with 1000. After each deformation, we automatically detect if there are flip triangles, and if so, we redo the deformation of the iteration using half the value for lambda. ILSCM guarantees that the deformation will not result in flips, and in practice, we always were able to meet the user constraints up to numerical precision. Here is another example with many iterations to satisfy the constraints. Our approach adaptively decreases lambda to find a value that results in no flips. When no flips are detected, the iterations make progress toward lining up the landmarks. In the last phase, we extract the mapping by rebuilding the mapping from the deformed parts. Since the mapping is expressed as body-centric coordinates, it can be transferred to the 3D patch and then to the full mesh. The mapping is extracted as body-centric coordinates from vertices of mesh A to faces of mesh B and vice versa. We will now show results from our mapping editing approach. Here, a realistic facial texture is used for qualitative evaluation. Our approach reduces texture transfer issues locally in the ear region. Several applications, such as morphing, rely on a mapping as well. Mesh A morphed to mesh B is unable to recreate the ear. Morphing with the updated mapping pulls the vertices to the right place. In this example, the mapping is adequate for morphing with respect to the body, but the mapping of the muzzle is wrong. Our approach locally adjusts the mapping for the muzzle, resulting in a much more realistic morph. Here's another example for which the initial mapping is globally good, but is locally misaligned in the head region. We use full landmarks to improve the mapping. We made a comparison among limb, slim, kp Newton, and our ILSCM approach for mesh deformation. The red dots are the initial positions, while the green dots are the final positions. When we zoom into the deformations, limb, slim, and kp Newton severely distort the mesh in face region, while with ILSCM the features of the face are much less distorted. Here's a qualitative comparison between limb, slim, kp Newton, and ILSCM to conduct the mapping deformation, minimizing the LSCM energy for all methods. The distortion we just saw in the face region for limb, slim, and kp Newton produces a weaker improvement of the mapping compared to ILSCM. We kindly refer the audience to the paper for additional comparison. Our approach has some limitations. For mapping adjustment, we were always able to satisfy the constraints up to numerical precision. When considering the more general problem of deformation, it is possible to design user constraints for which our approach as well as state-of-the-art methods all fail to satisfy the constraints. This is an inherent limitation of our approach and current deformation methods. Here, with this landmark configuration, moving the landmarks to their final positions make it hard to converge without any flip faces. Limb, slim, kp Newton, and ILSCM are unable to meet the landmarks constraints and avoid having flipped triangles at the same time. This is another limitation. In our approach, we do a segmentation based on user identified local regions where the mapping needs to be updated. Here's an example when two clusters of landmarks should be selected manually to improve the mapping on the nose and neck regions separately. Our approach solves an important practical problem and offers three novel scientific contributions. The first is a practical approach for local surface map editing, which we showed using both qualitative and quantitative metrics provides better results than other state-of-the-art methods. The second involves a compact segmentation which results in a compromise between a low distortion flattening and a low distortion deformation when aligning the landmarks. The third is a new deformation approach, ILSCM, which preserves conformal energy better than other state-of-the-art methods, and that has theoretical guarantees preventing the introduction of foldovers. The benefit of this approach is to be general and not limited to a specific initial mapping. Our local editing led to an interesting question which opened many avenues for future work. One such prospective area is higher level landmarks such as lines. This will lead to challenges in terms of easing the interactive placement of these lines on both meshes, but will provide a better set of constraints for the deformation. Another avenue for future work would be to automate the clustering of regions for the editing based on landmarks. Thank you for watching.